Okay, we're almost out of chapter 7, getting really, really close. Patterns were kind of the majority of it. We're going to talk about local variable definitions. It's an interesting thing because I think with object-oriented programming, which you guys know a lot about, a lot of these sorts of scoping issues became so obviously inherent and built into the languages that I don't know if you have to think about this as much as I did when the world was imperative. Because in an imperative world where you just sort of everything was function calls, procedure calls, you would have variables, local variables declared. I guess you still have that, but local variables declared. But everything was in main. Everything was essentially just a subset of this one big thing called main, and you didn't have that kind of modularized buckets of stuff with a little bucket with its own variables and then constructors on that, and and you had to like be explicit about making those visible. Well, we had to live and die by sort of scoping rules, right? What could be seen where, when, and where, essentially where in the program could you see a certain variable, right? And that's kind of what this is about. You've got the ability in ML to do that sort of thing, okay? And so you can actually use, we talked about before using val to define a variable, right? I mean, to define a value, sorry. And you could do it at the very top, and then once you define it, you can kind of see it, everywhere. But this is really about limiting that scope, okay? And this is the definition, kind of how that thing works, the grammar. The keyword is let, and then there are certain val definitions, which we'll show you, and then the keyword in, and then there comes an expression, and then end. Now, and as you guys know, I'm not a massively experienced ML programmer, so I don't know how extensively people use this in practice. It does give you an introduction to the concept of scoping if you haven't really thought about that much in the past. But I don't know, and I also don't know how big those expressions tend to get. The example here is actually very tiny. So here's an example, right? You got the keyword let, again. You got val x equals 1, val x y is 2, and then here comes the in, and then there's the expression x plus y. And so what this little kind of screen grab from SML is showing you is the value of it is 3, right? Because x is 1, y is 2. Inside that, I add x and y together, I get 3, and that makes perfect sense. Then I just simply say, what's the value of x? And it goes, I don't know, right? And that's just an example or an illustration of the concept that there's a scoping rule in place and we can't see it. So that's really the punchline. We like to look at proper indentation, which makes a lot of sense. You look back, that's not super readable, and this is a bit more readable. So I see the let, the in, and the end. Those are the keywords. I stack up the values. I can put semicolons or not, apparently, after each of those values. Personal choice, but that's the same thing. Okay, here's another example where whenever you've got like really long expressions, like seconds are defined as hours, days times hours times minutes times 60. Well, sorry, hour. Basically you take days, and every day has 24 hours. Every hour is 60 minutes. Every minute has 60 seconds. It just gets kind of grungy. And so what this allows you to do is set. So we got days to milliseconds is what this function is trying to be. Days to milliseconds. So if I pass in a real, right, as the number of days, I take that days, I multiply it times 24.0. You can tell that that's a real, right? Because I start doing mathematics and multiplication with real numbers. So hours is days times 24, minutes is hours times 60, seconds is minutes times 60. And then I'm really only hanging on to the expression seconds, because what I've really done is concatenated all of that. And I could have just as readily said, I could have just simply said equals 24 times, days times 24 times 60 times 60 times 1,000. Or I could have worked all that math up and made one big number and then just multiplied it by that big number. But this gives you documentation. This gives you a kind of a readability factor in terms of the code that you get to see And that's kind of the main reason. Yeah, as you notice, these local values, hours, days, minutes, we never even use them. It's only seconds that we use. So, I mean, this is an example of where you might want to use something like that. And then here we use the let in conjunction with patterns. Now this one is actually fairly spiffy. This is, I don't like the name because I just think that, you know, have H-A-L-V-E. I always want to say halve because when you say have, you think of H-A-V-E, right? The haves and the have-nots. So I don't like it because it's just when I say it, it doesn't sound right. And you want to say half. I might even call it half, which is more like the noun than the verb, but we're stuck with that for now. So here we go. What you should notice is, I think you can see my mouse there, you should notice is 3 patterns, okay? I've got a pattern in which it's only nil, I got a pattern in which it's only 1 element, and then I got a pattern where it's 2 or more. If you look at this, this is a pattern where it's 2 or more elements, okay? I think you should be able to see that. There it's nil, there you can see that that's a list with only 1 element. But here you can see, remember this cons, the colon, that basically appends an element to a list. So when you use this cons operator, the far right guy is a list, and then the next guy gets appended, and the next guy gets appended, and when you're done, it's a list, okay? And the parens, again, are just for precedence. So as opposed to, you know, a tuple. Remember that a tuple, you know, can't have just 1 element in it. So what we have here is this definition with 3 patterns. And if you can actually tell, in a sense, already one of the things you're going to do. If it's nil, then what this function's trying to do is take any list and just cut it in half. Put half over here, half over there, okay? And so if the list is nil, then, you know, the left half is nil and the right half is nil, or you know, half number 1 is nil and half number 2 is nil. Done. And that's our base case. That's the part that we bounce off of as we consume this thing going down. That's the part that we bounce off of. When it's only 1 element, I'm going to say, okay, the 1 guy is over on the left, and then the rest of it's nil. Now, this is interesting because if you look at this, one way to think of this is as the nil pattern is the case when there's an even number in the list, right? Because we're going to chew up, you know, 2 every time, all right? And if it's even, we're going to end up with nil, and if it's odd, we're going to end up with 1. But these are basically both the base cases in a sense, right? Because this is going to go chunk, and it's not going to go recursion anymore. It's not going to go lower. So both of these are base cases. You know, the nil case for when it's even, an even number of elements in the A case for when it's an odd number. When it's 2 or more, then what I do is I define this halving function to be with the input A, B, and C and CS. Remember again, the cons function, this is a pattern, and what it allows me to do is say, essentially this matches any pattern where you've got a list of at least 2 elements, okay? And what it does is it says that we're going to call the first guy A, we're going to call the second guy B, we're going to call the rest of it CS, okay? Then what I can do is I can say let val, I create this val, xy equal have CS. This is the part where I actually make the recursive call. I take CS, which is the rest of the list, and I call have, all right? And what I'm going to wind up with is half of that list is going to be bound to X. The other half of that list is going to be bound to Y, all right? So now I've got, within the context of this expression, I've got a local value of X and a local value of Y, which is X is half of the remaining list and Y is the other half of the remaining list. Now I can take A and append it to X, and I can take B and append it to Y. So I've basically taken 2 of them off, split the rest, and then stuck those 2 back on the 2 halves, all right? And then what that does is it returns back a list, right? Each of these is a list. That's sort of a half of the list. I just want to say it's a little funky when we look at the code here. You're going to find that the way the list gets created, it follows what the code says, but it is a little funky, and we'll have to kind of look at it. But anyway, once again, I just want to say this use of patterns is really, really smooth. All I have to do is say, it looks like this, and then I automatically get a local, value called A, a local value called B, local value called CS. I can just, and I can do stuff with that. If you can get your head around the recursive thinking, it really does, they call it deconstruction, but I call it breaking the thing down, but it really does give you a very easy way to deconstruct or to break this thing down into the smaller versions of itself if you can get your head around that concept and let go of the iterative approach, okay? Here's that thing working. All right, there it is again. That's the exact same code. First of all, we've got ML wants to tell us what type this thing is. It's a function, and it takes a list of anything. It returns a tuple with two lists in it, okay? List of anything. Remember that what that is has to match, but I do have with one, a list that just contains the element one, and then it evaluates to the list with one and the null list, the nil list, okay? Which is an int list, a tuple, which is an int list and another int list, okay? All right, I can do a have with one and two, and this is a situation where I've got two or more, and it's going to split those up, put a list with just one over here and a list with just two over there. Now we get a longer one, 1 through 6. And what's interesting when you note this is you actually get the odd numbers on the left and you get the even numbers on the right, which is kind of funky. You're like, why? And if you look at it, what you kind of see is that every single time, if I look back up the code, I peel off the first two elements, right? So I'd peel off 1 and I'd peel off 2. The remainder of the list, 3, 4, 5, 6, is CS. I then do the have on CS, and that kind of works, goes all the way down. We'd have to kind of stack this up to see how it goes all the way down. And then when we're done and we got a half of CS, we stick A on the first one and we stick B on the second one. In this case, B, because we passed it 1, 2, 3, 4, 5, 6, it returned every other one in the first list and the other every other ones in the right one. So this code is always going to return every other one, starting with the first one in the left list, and the remaining every other ones in the right list. That's just how it's built. So you kind of get the idea. I hope that makes some sense. And let me just say this too. It would really be smart of you, if you want to learn this stuff, just to go type this in. Go drop that in. It's in the book. Well, I'm going to assign it anyway. It's in the book. Go type it in and then start playing with it. Start mixing it up. Change something. See what happens. Don't just do the baseline thing. Play around and find where does it break. What can you do? What can't you do? Things like that. Okay, that's where we're going to stop this one. The next one coming up, the last sort of kind of substantive new topics section of chapter 7 is concerns nested function definitions. That's what we're going to come back to. And there's also then, within that nested function, we've got a really elaborate merge sort sample that we can walk through. I'll have to figure out whether I want to walk through that here in the podcast or in class, but it's certainly there in the book, and you should walk through that. But anyway, we'll stop here for now.